Hello everyone, this is Hongshu Danny In from NVIDIA Research, and today I will introduce our work called ViT, Adaptive Tokens for Efficient Vision Transformer. Transformers have yielded state-of-the-art performances in many NLP as well as vision tasks. However, due to its extensive computation of attention across all its tokens, the model remains quite large and slow. If we take a closer look, almost all current transformers use a fixed amount of computation across all its inputs. However, as humans, we really do it quite differently, as we are able to very quickly adjust our effort depending on the task complexity. For example, we can quickly tell it's a tiger on the left versus this camouflage deer on the right. Therefore, in this work, we challenge the current paradigm of ViT as shown on the bottom left part that processes all inputs with all computation, and instead we propose an adaptive paradigm that allows the transformers to adjust its computation depending on input complexity. To do so, we propose ViT, Adaptive Inference for Efficient Vision Transformer. The main idea is we want the transformer to halt tokens deemed redundant for the task only after the first few layers, and process more on the informative tokens with more deeper layers. Given the importance of tokens vary greatly across images at different patch positions, the entire process has to be done adaptively by nature. Via our proposed method, we observe the network is surprisingly good at this task, and it focuses only on informative regions as shown by these quick examples on the bottom. To gain more details on how to enable adaptive inference for tokens, we equip each individual token with a halting probability and form an adaptive computation time paradigm with mean field aggregation. For each token, once the accumulated halting score reaches 1, the token will be dropped and stopped for future layers. Note that this dropping happens before tokens enter the next transformer block, and therefore requires no modification or redesign of the block, offering direct speedups. Please check our paper for details. The associated loss term contains 3 different terms. The first task loss aims to achieve higher performance such as accuracy, whereas the second term is the pondering loss that penalizes the token depths to save compute. It does so via layer and remainder penalty. However, a single alpha p for pondering loss is weak in guiding towards a target budget, and to accommodate for this, we introduce a distributional prior that guides the learning halting probability towards a target stopping depth. Halting of each token is based on one existing embedding position, rescaled and rebiased into a sigmoid gate, and therefore impose no extra parameters or network to learn its halting probability. We observe the network is very smart in token dropping. Here we show ImageNet 1K analysis with each pair a left original image, and on the right is its token depth distribution. A whiter region means it's deeper processing for tokens. We can observe that the computation distribution really aligns with image semantics as well as human perception. We also compare with prior literature in both NLP as well as vision tasks for adaptive inference, where we show consistent performance improvements. Compared to the very recent inspiring work of dynamic ViT, our method captures better semantics and offers improved overall efficiency. As the method is able to drop redundant tokens in between transformer blocks, it enables direct speedup of vision transformers on existing GPUs, such as what we show here of 40 to 60% speedup improvements, without any hardware or software modifications or transformer block redesigns. The main takeaway of this work is we show the viability of transformer to do adaptive inference, and the surprising fact that without extra learnable parameters, the network is surprisingly good at this task and focuses only on informative regions. Here is the link to our paper as well as project page. Thank you, and please stop by our talk as well as poster sessions.